Okay, I'm going to go through 3 different things in this video. So the first thing is the concept behind sine and cosine waves. Second thing, I'll go through some applications. So basically what they're used for in real life. You can skip that part if you don't care. Third thing is the basic math behind them. So first I'll explain how they exist, right? Like how can something that looks like this happen from math? Now, sine wave actually comes from the unit circle. Same with the cosine wave. They both arise from the unit circle. And if you study the unit circle, you know that the y coordinate is sine and the x coordinate is cosine. Now let's draw a graph really quick. Up here is going to be +1. Down here is going to be -1. And the reason why we're using 1 and -1, because the unit circle's radius is 1. Right? Now let's say you start here at 0 degrees and you travel along the unit circle. As you travel, the height of your point on the outside of the unit circle, it changes, right? And that's basically what the sine wave is. So as you travel along the unit circle, sine goes up to 1 at the peak of the unit circle, and then it starts to go down again halfway through, and then it goes down even further and then back up again. So basically these points on a sine wave, they basically just represent the distance, right? The value of sine, the y coordinate. Now, how are you supposed to graph cosine waves when cosine is the x coordinate, right? Your graph would look like that. So basically, what a cosine wave is, it's the unit circle tilted on its side. So let's say this was the x axis, right? And then this is the y. When you spin it this way, this becomes a new x. So down here would be like -1. This is 1. This is your new 0 coordinate. And that's basically how you do it. This is what's called a phase shift, which I'll explain later. Now we can graph it. Unlike a sine wave, which always starts at 0, cosine waves always start at 1. So, of course, it represents the height of x coordinate as you travel along the circle. So it will dip down very low down here, and then it'll rise back up again like that. So just to recap what I said, sine waves have a shape like this. Cosine waves have a shape like this. So sine waves represent the y coordinate and cosine waves represent the x coordinate. So I'm going to explain to you what the period of a wave is. So let's say you have a sine wave, right? One period of the sine wave, which is basically saying one cycle of the sine wave, is one revolution around the circle, which is 360 degrees or 2 pi's in radians. So the period is usually 2 pi. So if it repeats again, it's just gone another 2 pi. Same with cosine waves. Okay, time to explain some math behind the sine wave. Now, this applies to cosine wave as well, okay? Everything I'm about to say here. There are a few properties to the wave. Just like how you have a line graph or a parabola, there is an equation for it. So, usually it'll look something like this. This looks pretty complicated, but I'll go through it nice and slow. Now, first, A is amplitude. Now, amplitude is always absolute value, which means it's always basically just positive. And it basically decides how high the wave is going to go. So let's say your amplitude is 3. Then you multiply the peak by 3. So these ones would go away and become 3. Next we have K, which is frequency. And frequency is pretty simple. Remember how the period is 2 pi? Frequency is basically how many times your graph repeats itself in this period. So if it repeats itself twice within 2 pi, so let's draw one here. That means the frequency is 2. It's 2 times faster than a wave that completes its cycle once in 2 pi. Now, what if it was slower? So it took twice as long. Then the frequency would be 1/2. It completes 1/2 of a cycle every 2 pi. Now here's the period formula as well, because it uses frequency. Now let's say your frequency is 3. Your period would be 2 pi over 3 instead of 2 pi. So it does depend on the graph, but if a sine wave is just this basic equation, or cosine wave, the period is always 2 pi, because that's one revolution of the unit circle. Now let's go on to the B. Now this part's a little more complicated, but it's called the phase shift. Now the phase shift is basically how far forward it's going to get pushed or how far backwards it's going to get pushed. For example, let's say you have a phase shift of pi over 2. Let's get rid of this wave here. Let's redraw this graph. Messed it up. Let's say here is pi, right? Because the period is 2 pi, so 2 pi, pi is halfway. If your phase shift is pi over 2, it means it's going to get pushed pi over 2 backwards. Now, if it's negative pi over 2, your wave starts at positive pi over 2. So, for example, we'll just say it's negative pi over 2, right? Then instead of your wave starting here, it starts here. There's a little gap here, right? That's a phase shift. Now time for C. C is your vertical shift. It's a lot simpler than phase shift. It's basically how far it gets pushed up. So amplitude gets applied first, alright? So you do the multiply by 3. And then you apply the vertical shift. So let's say your vertical shift is 2. Then this 3 here would become, hang on. Then this 3 here would become negative 1. Because negative 3 plus 2 is negative 1. And up here, this 3, it would become 3 plus 2, which is 5. So the whole thing's just been shifted up by 2. Of course, it's going to look a little different. The center line here, it'd actually be pushed up as well. And the graph would be drawn like this. Now there's one more thing. What if the amplitude is negative? Well, if the amplitude is negative, all you have to do is... Okay, let's go back to amplitude being 1. Let's say your amplitude is negative 2. Your things become negative 2, right? But actually, the graph gets flipped. So it gets reflected. It goes upside down. Oh, that was horrible. It goes upside down. So usually it'll look like this, right? Now it'll look like this. For cosine, usually look like that. Now it'll look like that. So negative amplitude flips the graph. Okay, I know that was messy, but this isn't an in-depth tutorial. It's just kind of to help you understand this kind of thing. The concept, right? Now we're going to move on to some applications of these waves. How they work in real life. You don't have to watch this part, but I just think it's cool. Now, of course, you know about sound waves, light waves, so I'm not going to talk about that very much. But just know that frequency affects things like color or pitch, and amplitude can actually affect things like brightness and volume, right? Now, let's say you have a spring, and on this end of the spring, you have a block. It's a pretty heavy block. Say you use your finger and you push it down. You can model it as it bounces up with a sine wave. So let's say you have your graph. Let's say this is the motion of the block as it moves up and down. So you push it down and then it bounces back up, comes back down. Let's say it bounces up and down really fast. Quite a lot of times. Look like that. Another interesting way to use it for modeling is actual data graphs as well. So you've seen the data graphs that are like this, right? Like, you can actually use it for things like population. So let's say you have dogs and you have, what do dogs eat? I don't know. Let's say they eat cats. Now let's say the dog population starts up here and it dips. And the reason why it might dip is because the cat population goes up and they fight and they die or something. I don't know. I just hope you get my point. You can use it for a lot of things, not just physics like the sound waves, light waves. Another cool thing is, for example, a guitar string, right? Say this is your guitar. Let's say you pluck a string with your finger. As it vibrates up and down, you can model it. Alright, in the description, I've got a Discord and I've put every single topic that I teach and I've made a worksheet for all of it. It's completely free. You can go join if you want some extra practice.